Hello, everyone. In today's lecture, I will introduce the weak-compactness theorem for Ricci shrinkers. Now, in this mini course, we have discussed the classification for low-dimensional Ricci shrinkers. Specifically, that means for 2- or 3-dimensional Ricci shrinkers, essentially they have only finitely many types. But this is not true for higher dimensional Ricci shrinkers. Even for 4-dimensional Ricci shrinkers, the classification is far from complete. So one strategy is we try to derive some uniform estimates, like what we did before, that is by deriving some estimate for the volume or other non-local collapsing properties and how this is related to the pair mass entropy. Another strategy is we regard all those possible Ricci shrinkers as one moduli space. So recall that the Ricci shrinker is a triple with a potential function f and a base point p, where p is the minimal point of f, satisfies the Ricci f, that is the Ricci curvature plus Hessian f, is equal to the g over 2. Now, we regard all those Ricci shrinkers as one moduli space M. Then we discuss its compactness. So natural question is this moduli space M compact? Now, at the first sight, the answer is negative because, first of all, it's possible that it will develop some singularity when you consider the convergence. Second of all, it's possible that some collapsing behavior might happen. So the higher dimensional Ricci shrinkers might collapse to a lower dimensional Ricci shrinkers. So generally speaking, the compactness theorem might not be true. So we have to develop some other weaker theorem, that is so-called weak-compactness theorem. Here, when we talk about the moduli space, we always assume that the convergence or the topology is with respect to the Gromov-Hausdorff topology. Okay. Now, what we are trying to derive is if we have a sequence of Ricci shrinkers of the same dimension, let's see, Mi, Gi, Fi, assume that they converge in the Gromov-Hausdorff sense to some limit space, M infinity, D infinity, P infinity. What nice properties can we derive from this limit space? First of all, we have to make sure at least this must be a metric space. Okay, now with this question in mind, we first of all recall some other weak compactness theorem for a sequence of Romanian manifold. Now, the first one is the so-called the Romanian manifold with section curvature bounded below. So assume that we have a sequence of Romanian manifold such that for all those metrics, the section curvature is bounded below by negative lambda. Then we try to show that we can find a subsequence so that it converges to a limit space. So by taking a subsequence, it converges in the Gromov-Hausdorff sense to a limit space. And this limit space also has sectional curvature bounded below in some generalized sense. So it's called the Alexandrov space. Notice that here, the Hausdorff dimension for the limit space might be smaller than the dimension n. Now, another theorem is we replace the sectional curvature condition with the Ricci curvature condition. Here, I will only consider a special case. Now I assume that our Riemannian manifold has Ricci curvature bounded above and below. So we see the norm of Ricci curvature is bounded by K, and we have some non-collapsing condition with respect to the base point. So here we fix the base point Pi, and we assume that the volume of this BGI Pi1 is bounded uniformly below by some positive number V0. Now with those two conditions, by the Cheeger-Coding neighbor theorem, we can show that by taking a subsequence, it converges in the Gromov-Hausdorff sense to a limit metric space. So first of all, this is a metric space. Moreover, this limit space has some nice property. First of all, it has the same Hausdorff dimension n with the original sequence. That means the collapsing doesn't happen. Moreover, the limit has the so-called regular and singular decomposition. So it can be decomposed as the disjoint union of R and S, so that any point X belongs to R if and only if the tangent space at X is equal to the Euclidean metric. Now, at the same time, we can show that if X belongs to the singular part, then the tangent space is actually a metrical. Tangent space is a metrical. Now, if at a regular point, any tangent space is a Euclidean space, but at a singular point, the tangent space might not be unique. Anyway, we can show that on the regular part, it actually can be equipped with a Riemannian metric, which has the lower regularity than the original Riemannian manifold. So here I list some facts in the Cheeger-Coding theorem. So first of all, the regular part R is an open, possibly incomplete Riemannian manifold with a C1 alpha metric. So in some sense, this metric can be regarded as a limit for the original smooth metric GI. So in some sense, GI converges to G infinity in C1 alpha topology. Now, why this fact is true is because around any point at the regular part, we can choose the harmonic coordinates. So under the harmonic coordinates, we can write the Ricci curvature as the negative 1/2 Laplacian Gij plus some lower order term. Then as long as the Ricci curvature has a bound, then we can show that Gij has C1 alpha bound. Then this sequence of metric can converge in the C1 alpha topology to a limit metric. So this limit metric is well defined on the regular part. So I want to mention that if originally we assume that, so if we assume for the sequence GR, it satisfies the stronger condition, that is the Ricci GI is KGI. So we assume that this sequence is a sequence of Einstein metric, then not only we can obtain the C1 alpha bound, we can use the bootstrapping technique to get a C infinity bound. That means that this sequence metric GI converges smoothly to a G infinity. Moreover, since G infinity is smooth, it also satisfies the Einstein equation. So Ricci G infinity should be K G infinity. So that means on the regular part R, the limit metric is an Einstein metric. Okay, now what about the singular part? It was proved by Chigger and Neighbor that the singular part can be well controlled. In fact, they show that the Hausdorff dimension for the singular part is less or equal to n-4. So this is the so-called codimension 4 conjecture. Now, moreover, it was proved by Coding and Neighbor that the regular part is geodesically convex. So R is geodesically convex. Now it means that for any point, any 2 points on the regular part, we can connect them by minimizing geodesic, which is entirely contained in the regular part. So let me draw a graph. So this is the regular part. For any 2 points, there exists a geodesic. Now, by this condition, one can easily show that the limit distance is actually agrees with the distance induced by the G infinity. Basically, one consequence is the D infinity, that is distance on the limit space, agrees with the distance function induced by G infinity. Okay, now we try to obtain a similar theorem to the Ricci shrinkers. So in some sense, we try to generalize the Chigger coding theorem to the setting of Ricci shrinkers. However, we immediately obtained some problems. The reason is for the Chigger coding neighbor theorem, we have to have some restriction on the Ricci curvature. So at least we need to know the Ricci curvature is bounded below. However, this is not true for any general Ricci shrinkers, because the only condition we have is the Ricci F is equal to G over 2. So Ricci F is bounded. It doesn't imply Ricci curvature is bounded. So this is a natural obstruction. However, we know that the Ricci curvature, the Ricci shrinker has the Baker-Emery Ricci curvature to be bounded. So we try to relate this Baker-Emery Ricci tensor to the original Ricci tensor. Now, how can we do so? We try to use the conformal transformation to achieve this. But before I talk about that, let me set up the problem. So here, let me define a moduli space, MAN. Now I consider all those Ricci shrinkers satisfy the entropy is bounded below by. So here, first of all, we require that all those Ricci shrinker has the same dimension n. Second of all, we require that the entropy is bounded below by -a. Notice that here, the last condition is equivalent to say all those BP1 has uniformly volume lower bound. So this was derived by the last lecture. We show that e to the mu is comparable to the volume of the unit ball at P. So this somehow equivalent to some non-collapsing assumption. So this is the non-collapsing assumption. So the reason for this is we try to make sure that the limit space, if it exists, has the same dimensional, same dimension n. Okay, now with the entropy to be bounded below uniformly, we have the kappa non-collapsing condition. That is, for any Ricci shrinker in this moduli space, we have if scalar curvature is bounded above by r to the -2 on BQR, then the BQR is bounded below by kappa times r to the s. So here, the last kappa depends only on A and N.
Okay, that means this moduli space has uniform kappa non-collapsing property. So first of all, we will show that in this modular space M and A, we will have a limit space. So basically, we will have the ball packing argument. The limit space exists because we have the volume doubling property. So recall that for any positive number D and BQS in the function, the region when f is less or equal to D, we have the following volume comparison theorem, that is BQ, I'll use the BQR. So BQR over the BQS is equal to less or equal to some constant C, which depends on N and D, then R over S to the N. Here we require that R is greater or equal to S. So here, this is the uniform property which holds for Ricci shrinkers. In particular, we have volume doubling property. That is, if we fix our point P as the base point, then we can show that by taking a subsequence. Then for any sequence, Mi, Gi, Fi, Pi in our moduli space, it converges in the Gromov-Hausdorff sense to a limit space. So I'll use the D infinity as the limit distance. So this is actually follows from Gromov's famous work, that is the ball packing argument, as long as we have the volume doubling property. In particular, that holds for any Romanian manifold with sectional curvature bounded below, or even weaker, as long as we have the Ricci curvature bounded below. Okay, now as long as we have a limit metric space, the question is, can we have a natural regular singular decomposition? So just like the Chigger-Coding neighbor theorem, can we define a decomposition by regular and singular part? Now here, the difficulty, as I mentioned, is we lack the Ricci lower bound and upper bound. So we cannot directly show that we cannot directly show that the tandem cone even exists. So here, we need to do some local analysis. So the key idea is we try to perform a local conformal transformation. The result for this transformation is we can make at least locally the Ricci curvature is bounded. Now here we fix a Ricci shrinker, for example, because all those estimates are uniform. So one is enough for instance. So let's say we pick any Ricci shrinker in our moduli space. So with the base point P, let me draw a graph. Here, this is a base point. Now I consider a point Q, which might be far away from this P. I denote the distance between P and Q by D, and I consider a small ball around this point Q. So here, I take a small ball with the radius, which is approximately D inverse. Now, what is the good thing when we restrict ourselves on this smaller ball? First of all, we know that because the scalar curvature is always bounded above by the potential function f, which is almost equal to d squared over 4. That means the scalar curvature increases at most quadratically. So if I consider the small bore with the radius r equal to d inverse, then we get a uniform lower bound for this smaller bore. That means we can show that the scalar curvature is bounded by, almost bounded by r to the negative 2 on this smaller bore BQR. Then by the no local collapsing theorem, we have the volume lower bound, that is BQR automatically is greater or equal to some constant kappa times r to the nth. So in this board, we have up to scaling a nice lower bound for the volume. Now, second of all, we can perform a local conformal transformation so that the geometric property in this small ball behaves nicely. Now, how can we do so? We define the conformal metric G bar as e to the negative 2f bar over n minus 2 times G. Here, the conformal factor is defined by f bar, where f bar is a renormalization of our potential function. That is, f bar is defined by f minus its value at q. So this can be regarded as some kind of differential of this potential function. Now, what is the good thing about this new metric G bar? That is, by the formulas in conformal geometry, we can compute the Ricci curvature of this new metric, which is denoted by Ricci bar. So by some calculation, we can show Ricci bar is 1 over n minus 2 df bar wedge df bar plus n minus 1 minus fq minus f bar times e to the 2f bar n minus 2 g bar. Now, the good thing about this is there's no more Hessian term, because under the conformal transformation, the Hessian term is absorbed with the Ricci term, that by the Ricci-Schwenker equation can be simplified. Now, we can derive some basic estimate for this f bar. The reason is we know that from the identity gradient f squared is equal to f, we know that square root of f is 1/2 Lipschitz. From this fact, we know that the gradient f is almost equal to r on this small board. So on this BQR, let me check, sorry, it's r inverse. So if we consider the lower bound and upper bound for f bar, we know that the f bar is almost bounded by 1. So that is from the estimate for the gradient. So that means, in other words, if I restrict ourselves on this small ball, then the metric, the new metric G bar is uniformly bi-Lipschitz to the original metric G. Moreover, from this estimate, we can actually control the Ricci curvature. Now you can see from the right-hand side expression, we can derive that the Ricci curvature is almost bounded by r to the negative 2. So up to a scaling, that means the Ricci curvature is actually bounded. So that gives us a nice opportunity to apply the Cheeger-Coding neighbors theorem. Now, moreover, we recall that from our evolution equation for the elliptic equation for the function f, we have Laplacian f minus gradient f squared is equal to n over 2 minus f. Now we can rewrite this into the new elliptic equation with respect to G bar. That is, if I consider the Laplacian bar over the F bar, this is equal to e to the 2f bar minus n minus 2 n over 2 minus fq minus f bar. So now we obtained an elliptic system. So actually I will move this, I'll combine this with the expression of the Ricci curvature. So I'll move it here. Okay. I'll move the Ricci bound another place. Okay, now we have obtained a new elliptic system which involves the Ricci curvature after the conformal transformation and the elliptic equation about f bar with respect to the new metric g bar. Now, like what I have derived, we know that the Ricci bar is bounded above by r to the -2, so we can use the Cheeger-Coding neighbor theorem to obtain a limit space with respect to the conformal metric. So now recall we have a limit space by the Gromov-Hausdorff limit. So far we only know that the limit space is a metric space. Now, for each metric GI, we perform a local conformal transformation with respect to a point. So now I fix a point Q infinity in the limit space and take a sequence Qi in Mi, which approaches this limit point. Now, we know that the distance between Pi and Qi is almost the distance between P infinity and Q infinity. So we can say the dGi Pi Qi is almost actually converges to G infinity, P infinity, Q infinity. So for the latter constant, I denoted by D, and we set R to be D inverse. Now, for any Qi, we consider a small ball around Qi with the radius R. Notice that this R is independent of a subscript I. Now, for this small ball, we consider the conformal metric GI bar and the possible limit. Now we consider the BGI QIR, but now with the conformal metric GI bar with the base point PI, QI. So that will converges to a limit space U and D infinity bar and Q infinity. Actually, the set U can be regarded as a domain in the original space M infinity. However, the D infinity bar can be different than the original metric D infinity because that is induced by the limit of GI bar. Now notice that here, the GI bar has bounded Ricci curvature. Then we can apply the standard Cheeger-Coding neighbor theorem to get the classification or the characterization of the limit space. So notice that GI bar and GI are uniformly bielliptids. So this is one important conclusion we derived before. But for the limit space U with respect to D infinity, we have a regular and singular decomposition. This is from the Cheeger-Coding theorem. Cheeger-Coding theorem. Now, can we have a similar regular and singular decomposition. Notice that for the same U with respect to D infinity, so here the first decomposition is with respect to D infinity bar, and the second decomposition is with respect to D infinity. We have another regular and singular decomposition, where the regular part as before is defined that a point at which the tangent space is equal to the Euclidean space, while a point belongs to a singular point, while the conclusion is not for a singular point. Okay, now the important step here is we claim that the R is equal to R bar and S is equal to S bar. In other words, the regular singular decomposition with respect to those two different metrics are the same. So this is because we know that GI and GI bar are uniformly by Lipschitz, so that D infinity and D infinity bar are uniformly by Lipschitz. So those two are by Lipschitz to each other. Okay. Now, as long as those two distances are by Lipschitz to each other on the U, we can actually prove something stronger. That is, not only they are by Lipschitz, in fact, the by Lipschitz constant becomes nicer and nicer if we approach the base point Q infinity. So with more work, with more analysis, one can show the tangent cone. So the tangent cones with respect to D infinity and D bar infinity are actually isometric. So I'll briefly talk about why the last statement is true. So this follows from the definition for GI bar. So let's see that one more times. So G bar is defined by some conformal factor times G, where the conformal factor depends on the value for F bar. If we consider those points which is close to Q, that means the F bar is almost equal to 0. So the conformal factor is almost equal to 1. That means when we approach Q, those two distances induced by those two metrics are almost the same. So if we take a blow-up sequence to obtain the tangent cone, then those two tangent cones must be isometric to each other. Okay. Now, by the same characterization of the tangent cone, we know that those two regular parts and two singular parts are actually the same. Okay. Now, in particular, since those two decomposition are the same, we can use the Cheeger-Cody neighbor theorem to denote state that the Hausdorff dimension for our singular part is actually less or equal to n-4. So some consequence, that is the Hausdorff dimension of our singular part is equal to the Hausdorff dimension for the S bar, which is less or equal to n-4. Notice that here, the first equation holds because those two distances are by Lipschitz to each other. Okay. Now, in this way, we can give a nice local characterization of our limit space, which is the limit for some metric ball BGI QIR. Now, for the general global characterization, we can just patch all those local domains together, then we can obtain the global picture for the limit space. Basically, they have almost the same property as the Cheeger-Cody neighbor theorems. Here, I just want to mention one important fact, that is another consequence is on the regular part, not only we have a C1 alpha metric, but also we will have a C infinity metric. So that is GI actually converges smoothly to a smooth metric G infinity such that it satisfies the Ricci curvature equation. Ricci Schwenker equation. That is the Ricci G infinity plus Hessian F infinity is G infinity over 2, where we know that the F infinity is the smooth limit for the Fi. Now notice that this conclusion is similar to the result for the Einstein limit space. Now the only difference is since we do not a priori have a higher order estimate for Ricci curvature, we have to examine our local conformal transformation more carefully. Now let's go back to this elliptic system. Basically, by this original setup, we know that the Ricci bar is bounded and the F bar is locally bounded. So we can use the second condition to improve the regularity for F bar. That somehow gives us higher order estimate for Ricci bar. Then we can use the bootstrapping argument to prove that we have a uniform higher order estimate for both F bar and Ricci bar. So that means the metric is not only converges in the C1 alpha metric, but also in the C infinity metric, as long as we consider everything under the harmonic coordinates. Okay. Now, finally, I want to make some remark. That is, not only the regular part has a Ricci Schwenker structure, but also this is geodesically convex. So this is proved by Wang, Li, and Wang. So we have shown that the regular part equipped with the limit metric is actually geodesically convex. So this can be regarded as a generalization for a coding and neighbors result. In particular, it implies those two distances are the same. That is, the distance function induced by G infinity should be equal to the D infinity. Okay. But here I do not have time to go into details for the last proof. So this should be compared to the coding and neighbors proof. So finally, I want to remark that the reason why we care about the Ricci Schwenker limit space is we can use these structure theorems to analyze the higher singularity, I should say the region for high curvature part in a Ricci Schwenker. In general, we do not know whether or not a Ricci Schwenker has bounded curvature. It's possible that at some faraway points, the curvature might be very large. So by an appropriate point picking argument, hopefully we can show that the limit is another Ricci Schwenker with possibly some mild singularities. So by doing some further analysis on those limit space, we can in turn derive some properties for the original space. Okay, so this is the last lecture. Okay, thank you.